All right, recording is rolling. It is Friday, December 9. We're going to start the midterm review. We'll take a few days to do the midterm review. I'll tell you how the midterm is going to be formatted. I'm going to give you guys 50 multiple choice questions that are, these will be conceptual questions, multiple choice conceptual questions. Actually, you guys see this half page in front of you right now? This has been uploaded to Google Classroom for, I think about a week now. Okay, so a bunch of questions are going to come up here. Right, then there'll be 10 multiple choice questions that look a lot like some of you guys' quizzes, but it'll be from each of the sections that we've done. Right, so those will be 5 each, which is going to be half of the exam, so like half and half, right? Right, so we'll take a few days to do a midterm review, and we'll start that pretty soon here. Here's the midterm schedule. Now, since you guys are first period is going to be on Monday, December 19th. The very first exam you take is going to be your 7th period. That'll be next Friday. So you guys know your first exam is 7th period next Friday, right? Then after that, the week after that's going to be a 3-day week, just 2 periods each, right? And you'll kick off Monday morning with this class right here. Okay, you guys got that? Right, we're good. All right. Before I flip the screen, so we've got flip the screen here to my computer. Do you guys see this page also on your desk? It should be 2 pages. I give you guys, of course, all these multiple choice questions. Okay. And you guys see a bunch of graphs set up, right? And I put a X, B, and A in the units, right? Meters per second squared. Okay. Oh, you know what I should have put is time and seconds. That's what should go on this axis, right? Time and seconds, right? So we're going to do a bunch of review slides today. You guys are going to see a bunch of graphs, a bunch of scenarios. So I mean, you could just do this in your notes anyway, but this is a very convenient page where you can just sketch some graphs real fast as we're going along. Right? Here's that. All right. So switch my screen over here. 3, 2. All right. So show you some stuff on Google Classroom. Hey, midterm study guide. Hey, whoa. Where did it just go? It just disappeared. I clicked on it, disappeared. Okay. Well, anyway, the half page is on your desk. That's there. I'm almost afraid to click any of these other ones. Here, how about this? How about Spirit? Okay, so next week is Spirit Week. Oh, actually, I did open that here. All right, so that's right there. Monday is Hats and Socks Day, and there's a bunch of other days. If you're curious about that, that is on Google Classroom. And about to go through, okay, so the midterm schedule is on here. About to go through a PowerPoint with you guys that spent a lot of time over Thanksgiving put together. I just uploaded this morning a version that has animation on it. Like here, the one I'm about to pull up has the animation, right? Here we go. All right, there's the first slide. All right, so boom, there you go. Got a dot for every day of your life. All right. All right, so some slides on measurement. All right, orders of magnitude. There's 1,000 bubbles right there. Right, you guys know kilo is a factor of 1,000. Millis 1 over 1,000. So there's some examples: 1 kilogram, 1 millimeter. Right, 1,000 grams, 1,000th of a meter. Right, million. Ooh, tried to go for that. Right, so it's 10 to the 6. Right, and then 1 over 10 to the 6 is micro. It's 1 millionth of something. There's some examples down there. Right. Scientific method. Right, so you kick off with some kind of problem or question. Now, different textbooks have a little bit different versions of this. What's probably a good second step? Some kind of background research usually is thrown in there. Right. Once you know what you're asking and some idea what you're going for, what's good step after this? Hypothesis. Aha. Right. Sometimes defines like some kind of educated guess. Right. And then you want to conduct an experiment. There's the hardest scientific method right there. From that, you can get data, and you have to crunch that data, do some kind of analysis. In this class, we've constructed lots of graphs, find lots of relationships between variables. A lot of times with graphs, make equations, right? Some kind of equation relationship, okay? And then you can draw some kind of conclusion, right? Like the very last lab you guys did, the conclusion was the rotational inertia of that crazy pipe system was like 0.06 kilogram meters squared, something like that, right? Okay. There's the 7 base SI units, and you guys know that really this entire semester we've only dealt with the top 3, right? Kilograms, meters, and seconds, because you can rearrange this all different ways to be. Force measured in newtons is kilogram meter per second squared. Right, energy in joules, that's kilogram meter squared per second squared. Right, so right. Next semester we'll touch a little bit on these bottom 4, but
I don't think those will even come in to the AP exam at all. I think the AP exam that you guys get are really just the top 3, right? Just rearranged all different ways. Okay. There's the original definitions of those. It's way back in the day we talked about. Here's some universal constants. I think really the only ones that are relevant to you guys, gravity constant, 6.67 times 10 to the negative 11 meters squared per kilogram squared. Maybe the speed of light might pop up 3 times 10 to the 8 meters per second. Right. But anyway, there's some universal constants that nobody quite knows why they are, what they are. Interesting. Right? Scientific notation, crazy big mass of the Earth, bam, that's like 10 to the 24 kilograms. Mass of a proton, that's tiny, tiny, tiny. That's like 10 to the negative 27. Okay? You guys know negative exponents doesn't make the number negative, it just makes it really small, right? Okay. There's some prefixes. Here's more prefixes that are more relevant to you guys, right? So like the powers like multiples of 3. Go bigger or smaller. Accuracy and precision. So accurate is like, is it more correct? Precise is like how it translates to numbers is like more digits that you have. So if it said the speed of light is 3 times 10 to the 8 meters per second, right? That's true, but it's not very precise. If I want to be more precise, you can have like a whole string of numbers, right? Like more precision is going on. Dimensional analysis. You guys know here, this is one of the first things I taught you guys. Well, actually, you guys probably learned this in chemistry, right? It's a really powerful tool in chemistry. It's one of the first things we did in this class. And it's one of these tools that keeps coming back and being useful over and over and over again in this class. Even recently we use this, right? So if you had $1 billion and spent $1 a day, or sorry, $1 a second, right? How long? You could set it. Yeah, boom. Right, Jackson saying like 31 years. Boom, just like that. There you go. Yeah. So there's one way it could be used. I think radians to revolutions or revolutions to radians we did recently. You know, that dimensional analysis you can use. Scaling, right? Suppose you have a little tiny box down there and you scale it up by a factor of 3. Well, you have to say, what are you scaling up by a factor of 3? Suppose only one of the sides scales up by a factor of 3 and everything else scales up proportionally, right? So that's 3 times anything that's linear, right? Which is all those things. But you would need like 9 times the paint to paint it because that's 3 squared. And it could hold 27 times the water, right? If you filled it with water. That's to power 3 because 3 dimensions, right? Factor of 3, 3 dimensions, boom, boom, right? Algebra, right? You guys can do algebra, right? I mean, it's just like so fundamental to like so much we've been doing. Right? Quadratic formula. If you have any kind of parabola, which, hey, how about distance as a function of time when you are, or displacement as a function of time when you're in an accelerating environment, could make this opportune, right? That's a good one to memorize. Does AP actually give you that on? Let me check that real fast. I want to say they give you quadratic formula. I don't think they do, right? But anyway, that's a good one to have in your back pocket, right? To memorize before you graduate from high school. Okay. What's the equation of that line? Y equals mx plus b. Boom. That's a linear graph, right? Okay. A lot of graphs are linear. Okay. But not all of them, right? And here's like the basic common graphical relationships you guys have seen over so many labs in this class, right? Again and again and again. Right? You guys know what those look like? Right? If there's no relationship, it could be either horizontal or vertical line. It just means that one variable changes and the other variable doesn't care at all because there's no relationship. Right? Linear or direct, what's that going to look like? Boom, right? Line with some slope. M means slope in algebra, right? What inverse relationship? What's that going to do? One variable gets big, the other gets small. For example, Newton's second law of motion, F equals ma. If you increase the mass, you'd be decreasing the acceleration for some given force. Right? Mass and acceleration can have that relationship. Parabolic, that's like dropping a ball. How far does it go as a function of time? Right? This could be x versus t. Root relationship is just the opposite of that, right? If you just swap the variables, parabolic and root could just be like inverse of each other. Right? Sinusoidal. Has this one come up yet? Like the oscillating back and forth, right? It will in January, right? Because actually at this point in the class, we've covered all the AP topics except for one. There's only one topic we still got to cover, which is unit 6. It's like harmonic motion, oscillatory motion, pendulum swinging back and forth. There's some kind of oscillation going on. You guys are gonna see some graphs like this. Right? You guys know like sine and cosine graphs. Right? You get graph sine and cosine. Right? Maybe from pre-calc, maybe. Okay? Some of those. You guys know Pythagorean theorem. Area of a right triangle. What's the area of that blue triangle right there? Yeah, base times height over 2, right? And a lot of graphs in this class, you have to find some kind of area. And a lot of times they are triangle shapes, and you have to do that. Except the units are like time in seconds and height in like newtons, force in newtons or something like that, right? Right. You guys can find vector components. Okay, so here's the definitions of sine, cosine, and tangent. And here's like the common. I mean, you guys have probably done this literally hundreds of times in this class, right? B is c times sine theta, A is c times cosine theta. Right. So many times you guys have done this. Right? And can you guys extract the angle? Here's one way to extract the angle, right? Inverse tan of ratio of the sides. Okay. We got, here's the first set of graphs. So you guys got a paper in front of you. You can put some notes, you can dash off some graphs real fast. Car drives at constant velocity. What do those three graphs look like for a car driving at constant velocity? All right, whip them off real fast. Boom, boom, boom. Give you guys a few seconds. You guys should know what all three of those graphs look like for a car driving at constant velocity. Oh, I gave you guys a big old hint right here. Acceleration is 0 meters per second squared. Do you guys just draw boom, boom, boom? You guys just drew that, right? Okay. Well, you didn't have to draw the red and the green part, but you guys definitely drew those bold lines, right? Right, that's exactly what you just drew. Right? Constant velocity, right? Just like cruise control. I-95 at 70 miles an hour, not changing what you're doing. Can you feel how fast the car's going? No. Exclamation. My brother took journalism in college, and he was told that if you ever are a journalist and you have said exclamation marks, use wisely. You get 3 exclamation marks in your life. So maybe there's one of them. Okay. You can feel a change in motion, right? Okay. What's a linear acceleration? Can you guys complete this formula? Okay. Boom! Change velocity or change of time, right? Okay, but you guys know that. Hey, and then there was one that we didn't get to until about halfway through the semester. If you're changing direction, there's also an acceleration involved. But how's that formula go? Yeah, there you go. V squared over r. Okay. And centripetal force with the mv squared over r. That's actually where we started that, right? With the lab. Okay. You guys remember that? Okay. You guys know all this stuff, right? All right. 3 kinematic formulas. Could you guys write these from scratch? I mean, AP does give these to you. They write them a little bit differently than I've been typing them, but you guys should know these by heart just by using them so many times this semester, right? Right? You really should know these, right? Boom, 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 just like that, right? You guys know all those, right? If you don't know those for whatever reason, then I highly recommend just like sit down and like practice them and memorize them. Yeah, even though they're available on the exam, if you don't know them by heart, you'll be able to navigate them so much faster, right? Boom, 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 just like that. Right. Remember this principle: if you can identify any 3 variables, you can solve for the other 2. So you guys could solve for initial final velocity given those 3 values, right? Right. And by the way, that's what the answer ends up being. What's going on there? Okay. It's going to misprint. What that white's here. I don't know what all this fuzzy white stuff is over there. It's not supposed to be there. I'm confused. All right. So if you drop a ball off a cliff, you guys can make this whole table, right? Time's ticking 1 second at a time. Okay. Acceleration's constant. We're ignoring air drag. You guys know velocity goes at 10, 20, 30, 40, 50 meters per second. And displacement would change like this. Okay. Is that 1/2 AT squared right there? You guys remember the story of Paul Hewitt drops a rock in a mine shaft? How deep is the shaft? Count it 1, 2, 3, 4, 5. 5 seconds. About 125 meters deep. How'd you know that in college? Hey, 125 meters right there. Boom. Right? Now that's true for Earth, right? And of course, we're rounding a little bit because 9.8 is really close to 10 meters per second squared. Okay. 3 graphs. Boom, boom, boom. Can you guys draw those real fast for that scenario? Drop the ball off a cliff. Let's call it down positive. So down's the positive direction, right? We'll call the height at the top of the cliff 0.0. Okay. Can you guys whip off those 3 graphs real fast? Okay. You guys have seen this so many times in this class, right? Boom, boom, boom. Whip off those graphs. The table on one of the last couple of slides, you could just plot those like Cartesian coordinates and also make the graphs out of those coordinates from that table, right? Here, let me go back. Boom, that table right there. You could figure out this right here, right? Okay. Did you guys just whip off a parabola, a linear relationship, and a constant value? Boom, boom, boom. X versus t, v versus t, a versus t. Okay, you guys would know that, right? Great. So constant acceleration, just whatever the free fall of the planet is, which for Earth is like 9.8 or 10 meters per second squared. Okay. which means velocity picks up at a constant rate, and x versus t is going to be parabolic. Okay, and then that everything in red and green tells you the connecting relationships because all these graphs are related to each other. Guys, if you had one of those graphs, could you pretty much figure out the other two? Yeah. Okay. Okay. You guys got that? That's an accelerating situation. That's uniform acceleration. Okay. Ooh, throw a ball upward, throw a ball downward. So let's go back to the cliff. Right, so we're at the top of the cliff still. You guys see that cliff in the middle of the page? Okay. So the left three graphs are throwing a ball upward, right three graphs are throwing a ball downward. Let's still define down as the positive direction. So these graphs are going to be sort of upside down. That's how we normally do them in this class, right? Okay. Of course, AP might define up as positive and down as negative, and then be ready to feel that. But I always default to this. So the top of the cliff is 0.0, down is the positive direction. That means if you throw the ball upward, you're throwing it into the negative direction, right? And it's going to turn around and go back down. Okay. And if you throw the ball downward, it's already going into the positive direction. Okay. Give you guys a few more seconds here. Should be able to whip off those graphs. Boom, 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 boom. Okay. Right. If you know what you're doing, awesome. You need a little more hints. Okay. Suppose you do throw a ball upward. That means it has a velocity in the negative direction, and that's eventually going to change and become positive when it turns around and falls back down. Right? Okay. So boom, that's that graph right there. Right? Throw a ball upward. You throw it one way. Right? Ooh, what's happening at this point where it crosses the time axis? Ah, yeah, it's changing direction, right? Okay. So it's reached its maximum height at that time right here. Okay, it's about to turn around and fall back down. Okay. So then you could, okay, so constant acceleration. Okay. And then there you go, just like that. Oh, and also those two graphs line up like that, don't they? Okay. Boom, boom, boom. Right, now that's throwing a ball upward. Right? What if instead you went to the edge of the cliff and you took the ball straight down? Which this picture in the middle might apply to both of those, right? Because suppose you do like one after another sequentially. Like I throw a ball upward, it reaches the peak, it comes back down, and right as it's passing me at the top of the cliff, I take another ball and throw it straight down at the same speed. Are those two balls going to travel side by side all the way down to the bottom? Yeah, they sure will. Okay. So I bet these three graphs that you guys are about to draw right here are really just parts of the three graphs that are already shown, right? Did you guys just draw boom, boom, and boom, just like that? Okay. You guys see how those are slices of these? Like here, if I just start ticking the time at like whatever this time is right here, right? Just run with it. It's the same thing as those graphs on the right, right? Is that? Okay. And oh, look at that V versus T graph. V versus T is like very information rich, right? Because take the integral, you get how far. Take the derivative, you get the acceleration. Right? So do you guys see those two green? Actually, I think that might be the next slide. Yeah, it is the next slide. Okay. So blow that one up. Okay. You guys see V naught T is this rectangle, and 1/2 AT squared could be this triangle sitting on top of it. And if you add this together, V naught T plus half AT squared, hey, that's that first kinematic formula, isn't it? To tell you displacement versus time in an accelerating situation. Okay. Everybody good so far? See, we got any questions? Okay. Car brakes to stop. Boom. 3 more graphs. You guys, a few seconds to draw these graphs. Boom, boom, boom. Everybody draw some graphs. Car brakes to a stop. Did we do some graphs recently for a turntable slows to a stop, I think? Okay. I know that kind of similar to these, just this is linear, and the turntable is, of course, got rotational variables. But, okay, car brakes to a stop. Okay, so it's moving forward, its velocity is changing as it's braking. Should be some kind of acceleration because it's changing its velocity, right? Okay, you guys got those 3 graphs? You guys got those 3? Did you guys just draw boom, 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 just like that? Okay, so it starts off with a fast velocity, and as time ticks forward, going to the right, it goes to 0, right? Which means it has a negative acceleration. And displacement versus time, well, it's always going forward, so it's always like accumulating displacement, but at a slower and slower rate. Right. So those 3 graphs are related to each other. The green and the red tell you how those are connected. Okay. Right. That's good. For example, acceleration versus time. I see a negative rectangle. Therefore, the change of velocity, oh, it goes from positive value to 0. Hey, that's negative change. Okay. Cannon fires on a plane. Can you guys break that blast velocity into components, horizontal, vertical components? Right. And again, this is what I would venture to say you guys have probably done this hundreds of times in this class. There's some version of this, finding vector components. Okay. Did you guys just draw boom, boom, just like that? V cosine theta and V sine theta? Did that? I don't know, this smudgy block that maybe it's some kind of animation thing. Right, you guys have that? Cannon fires from the edge of a cliff. Right, so the projectile motion, right? How far it fell is 1/2 GT squared. Now that's strictly true if you fire it straight horizontally, right? If you didn't fire it horizontally, you have to do V naught YT plus 1/2 GT squared, and some version of that, right? But just pretty fundamental example, right? And how far it goes across, following that green shadow of an apple, is just V times T, right? X equals VT. Right? And then you can get its exact coordinate by saying, okay, well, here's what's due in the Y, here's what's due in the X. It's going to follow a parabola path, right? That's a parabola right there. See that? All right. Are you guys ready for a challenge question related to that scenario? Challenge question? All right. So that's the same scenario right there, right? I just changed Y to H for height change and X to D for like horizontal displacement distance. Right? Right. So we got this, we got this. Can you guys solve for blast speed? How fast the cannon blast? This was one of your labs way back in the day. Okay. Here, I'll guide you guys along. Start with the red one here, which is vertical information, how far it fell as a function of time. Solve for T. Solve for, because that'll constrain the amount of time that's been falling for, right? Okay. Can you guys solve for T? What did you guys get? T is equal to what? That would be true. Yeah. Yeah, I think it's what I'm looking for in this case. Yeah. Yeah, so get the vertical component velocity is square root 2g. Yeah, that's true. Okay. And then the time is that expression right there. Yeah, right. All right. And then how about this green bit? Let's go over here. Can you guys solve for V blast in terms of D and T? Oh, that's just a real simple. Just pull. Hey, can you guys substitute this T into this T and finish this off and solve for V blast? Now, you'd be getting V blast in terms of the height drop and how far it goes, horizontal displacement. Okay. Like you can measure those things. And this is exactly what you guys did for one of your labs. Okay. Let's finish this off. So sub that, boom, right in there. And you get finally V blast is equal to. Did you guys get that right there? Right? Or some version of that. It's a little bit different ways to write that. Okay. There's a fun one. I think I may have tried that with you guys one day. But whoops, I was going to ask you guys, but you guys would have said Newton's first law of motion is law of inertia, right? Object rests at rest. Object motion wants to maintain its velocity. Right? Unless there's an outside force. So if you ever see anything speeding up, slowing down, or changing direction, there must be a force on it. Right? What's the second law of motion say? F equals ma. Boom. Right? Actually, I really like this left form of it. Right? Acceleration is caused by a net force acting on a mass. Right? Go either way with that. Okay? How about Newton's third law? What's that one say? Forces are always equal and opposite. Boom, equal and opposite. So say this cannon blasts this cannonball. The cannonball gets a force on it. The cannon gets a force. It's the same force, right? The Earth and the Moon are pulling on each other with the same force, right? It's always the same force. Right? Now, why are the motions different? Why does the cannon barely move, but the cannonball? Huge change. In the Earth barely wobbles, but the Moon is like in orbit. Why? Because these objects have different masses, different mass, different inertia, right? Different effects. It's the same force. Right? Here's why same force. Boom. Right? Because suppose it was like 3-to-1 ratio. Well, okay. Nice visual to show Newton's third law of motion. Okay. Oh, Hooke's law. Can you write that as an equation? F equals kx. F equals kx. Some textbooks say negative kx. It just depends which force you talk about. I did one in black and one in gray, so it depends on your perspective. Are you talking about the force on the spring, the force from the spring? So if you ever see F equals negative kx, that could also be valid, right? Oh, you guys remember this graph right here? Right? F versus x, the slope is equal to k. What does k represent? What property of the spring? Spring constant. How stiff is the spring, right? You guys know the spring scales have different stiffnesses, right? And what does the area under the curve represent? Spring potential energy, right? Which is also the work done compressing the spring, right? Or stretching it. That was one of your quiz questions, actually. Free body diagrams. You guys remember these? There's some examples right there. So you're just drawing all the forces on an object. I double checked the definition. It says forces at moments like torques, but okay, focus on the forces, right? Spacecraft, constant velocity is 5,000 meters per second. Screaming through space, constant velocity. What forces are on that thing? None. Boom. Right. Because law of inertia is just going. Air hockey puck, constant velocity. What are the forces?
Gravity.
Yeah, it's got a weight and force from the air jets. Boom, boom, just like that, right? Wait, it's traveling to the right. Does there have to be a force going to the right? No, that's it. It's just coasting. Law of inertia again, right? How about an apple? Let's say pure free fall, which no air drag. What's the only force on it? Boom, mg. It's weight. So you can say mg like I pretty much always do. Yeah, if you do F sub g, like force due to gravity, AP will take that too. What if there's some air drag? Do you have this where the weight is bigger magnitude than the air drag? Okay. And what if it's been falling so long that it's picked up the speed so fast that the air drag's picked up so much that it's gone to terminal velocity? Right. Is that apple on the right in equilibrium? Yes, it is. Equilibrium might mean at rest or it might mean constant velocity. Right? Either of those could be equilibrium, right? But there's zero net force. Zero net force, just going front. I don't think AP asked anything about air drag, but there's a fun equation there. Coefficients of drag for different falling objects. Boom. There you go. You might see this one day in college. You guys take some science and engineering classes. Drop a ball off a cliff. Let's just do one graph of this. Let's do V versus T, and let's consider air drag. Right, so air drag is significant. Let's say it reaches terminal velocity before it hits the ground. What is that graph going to look like? Right. So you guys know what a regular V versus T graph looks like in a vacuum, right? Okay. How can you modify that to now include air drag? Yeah. Did you guys just draw boom that right there? Right. So it starts out like regular, right? Like as if it was in a vacuum, right? But then the air drag picks up and eventually it's going to asymptotically reach terminal velocity. Okay. And then it doesn't matter how long it's falling for, it's just at that terminal velocity. Okay. Everybody get smart? If you guys got any questions, let me know. Plane at constant velocity. How many forces? Yeah, okay, so there's an air drag. If there's an air drag, there must be a okay, yeah, maybe a thrust force, there's gravity force with weight, and is there a lift force holding it up? Are you guys thinking this word right there? Okay, there you go. Right? The weight and the lift, and then a thrust force and a drag. See, if it's constant velocity, that means equilibrium, so all the forces must be canceling out. And if you're sitting inside that plane, I bet you feel a lot like sitting in this classroom. Right? You don't feel any forces. Pulling a block, constant velocity. Constant velocity. Oh, that's also equilibrium, isn't it? Right, so all the forces cancel out. Are you guys thinking a weight down and a normal force up, and then there's an applied force from the spring and a friction force that's exactly countering that? Right, better. Okay. And those are equal and opposite, not because of Newton's third law of motion, but because of equilibrium. Right? The third law of force to each one of these is you have to also consider like the ground underneath it, and right, because Newton's third law has to do with like two objects interacting. Okay. But or how about this? The applied force from here, there's an equal and opposite force on the spring scale. You can say that, but you have to, right? But a single object, if forces are equal and opposite on a single object, is because of an equilibrium condition. Okay. Here's some common coefficients of friction. We've done a number of these, right? You guys know that that's the ratio of friction force to normal force, but it's also a material property. So once you know the materials, for example, if you know steel and aluminum, it's pretty well established numbers right here for between those two materials, right? Oh, these last three might be particularly useful if if you're like driving a car, right? Icy road, hardly any friction, right? Oh, block an equilibrium on an incline. All right, this one's a really important one. Can you guys draw the three vectors? And AP always says not components. So there are three vectors on that block to put it in equilibrium. Okay, can you guys draw those three vectors? What are the three vectors? It's weight, normal force, and friction force. Boom, boom, boom. Right? Weight, which you can't split into components, but if you do, then dash them, or you could just not draw them on the AP exam. Either way, right? You just imagine them, or maybe bring a lemon ink pen with you, right? UV light or something. The normal force and the friction force, right? And the normal force, straightforward is straightforward setup here is just going to be mg cosine theta. Okay? And friction force is going to be mg sine theta as long as it's equilibrium, which is either at rest or sliding down at constant velocity. Right? You guys have friction force is coefficient friction times normal force for the sliding case, right? Right. Elevator. If it's accelerating downward, isn't its weight more than the tension force holding up? And if it's in equilibrium, those two are the same. And if it's accelerating upward, then it's being pulled up more than the weight's pulling it down. Right? Hey, that's all we got today. Okay. Well, we'll more review next week. All right, you guys have a great weekend.
We'll get that.